Hey everyone, to start off with, what I'd like you to do is just if you go to our course website and to our chapter on evolution, the second video in our book of videos is this one right here, You Are Stardust, and I would really appreciate you watching that video before starting up these notes. So just to show you where that is, if you look on our course website, I guess if I go back to chapter 9, right, chapter 9 being our theory of evolution. Here's our book of videos, and um, video number 2 here, Stardust. Have a watch and then resume the video on the notes. So I think it's a great video when we sort of think about these questions, and rather than getting too philosophical, just it's a great example as well as talking about how matter really cycles, right? So how matter cycles through not just ecosystems on our planet, but it cycles through the universe. And so all that matter that exists out there is really just cycled from one form to another, including the living. So this section is an important section in the chapter of the theory of evolution to kind of put things in perspective with respect to the age of the planet and the time in which life has existed on our planet. And that's important. It might sound cheesy or maybe cliche to say, but it's important to understand our past in order to think about and predict and maybe understand what our future might look like. And it might sound cheesy, but it's really very true when we think about life, specifically how that life evolved. Also, to understand that our planet is constantly changing, not just the atmosphere and climate change, but even if climate change didn't exist, um, our planet is constantly undergoing change. And we can, in the short explanation of that, if we just think about plate tectonics, there's earthquakes, there's volcanoes, there's the shifting of these plates as our continents drift around the layers below that make up Earth. And so as this change occurs, well, life on the planet is going to change along with that. And so to put the sort of timeline in perspective, that we can say that Earth has been around for 4.5 to 5 billion years. So we say billion years, right? But how long is that? It's hard to envision, right? And there's different forms of showing that. This picture here in your book talks about Earth in a day. And if we were to envision a 24-hour clock, each of these being sort of an hour in time, if this represented time 0, and by the time we got back to 11:59, we'd be present day, and we would gone through 4.5 billion years, right? And so just to look at some monumental periods of time where, solid rocks start to form on our planet, prokaryotic life. So here we are, if we're 5 billion years old, prokaryotic life is developing kind of around maybe 2 in the morning. And from that prokaryotic life, photosynthesis developing at maybe 4 in the morning. And it's not until halfway through the day, 12 o'clock, in which we are getting free oxygen. So an oxygen atmosphere in which other life can start to evolve. And then now we can start to see eukaryotes. So remember we talked about the difference between a prokaryotic cell and a eukaryotic cell. So we have eukaryotes coming on the scene maybe at around 1 o'clock in the afternoon, right? So this is like noon on our 24-hour clock. So it's taken basically a half a day to get to the point where eukaryotic life and the life that gives rise to us comes on the scene. Somewhere maybe we've got 1 o'clock, 2 o'clock, 3, 4. So here we're at sort of 1600 hours, and multicellular life is coming on the scene at 4 in the afternoon, and then giving rise to animals, right? And I don't see, yeah, well, photosynthesis is evolving here, right? So plants are already on the scene. They would just be in single form, single cell form. And so at this point, when we get to multicellular life, this would be including multicellular plants, right? Multicellular plants eventually coming up with multicellular animals, maybe at about 8 o'clock in the evening, right? 8 o'clock or sort of 100 hours. And then we've got our land vertebrates, mammals, flowers, and then us coming on the scene shortly before midnight. To put it in perspective here, they've broken these various periods of time down into segments or sections. So the Precambrian being essentially from 4.5 billion years ago to about 500 million years ago. And then we are currently in the period of, or the time frame of the Paleozoic, which both of these represent eons. So think of eons as billions of years, right? And then when we start to look at eras, all right, eras are broken down into sections of an eon. So whereas you've got these different eons, which represent billions of years, eras are broken down and probably represent hundreds of millions of years, right? Some of these we might be familiar with when we start to get into sections of eras, which can then be broken down into periods. And periods might be just millions or tens of millions of years, right? Millions to tens of millions of years. And it just kind of puts things into perspective, right? In terms of the age of the Earth, age of the planet. And I'm not going to ask you about, when was the Tertiary period or the Cretaceous period, right, or the Jurassic, but it's really just to emphasize that the planet is an old place, right? Maybe some of these are familiar to you, Jurassic, we can think of the age of the dinosaurs, and they're falling in line about anywhere from sort of 200, 250, 300 million, right? Up until even 70, 80 million years ago, right? When the big meteorite hit. So, long and short, the age is old. The Earth is old. And so, how do we put this into perspective in terms of understanding when life exists, what the life was? So, we look at this, eukaryotic cells, prokaryotic cells, multicellular life, animals, etc. How can we be so sure? Because when we look at these different time periods, these periods are characterized, and this is one thing I would expect us to know, that these are characterized. Sorry, my pen stopped working there. So if you want to pause and write this down, these individual periods of time that can exist for tens of millions of years are characterized by the plants and animals in the environment that dominated that landscape, right? And so the question becomes like, how could we possibly know what kinds of plants and animals and how did the environment exist tens of millions of years ago? There's a number of different ways in which we go about learning about the past. And so one of the most fundamental ways we recognize and learn about the past is through, and I'm just going to fix my screen here. So one of the ways in which we learn about the past is through the fossil record, right? And it's one of the most significant tools that we use in learning about the past. And the fossil record represents evidence of the existence of an organism. And so one thing is recognizing that an organism exists or existed, but another thing is to understand when, right, this organism existed. So how can we figure that out? Well, one way in which we can figure out when an organism existed is what we call relative dating. All right, and so relative dating sounds like a bad sitcom, or something that we probably shouldn't practice. But in the world of geology, relative dating determines which fossils may be older than other fossils based on their position. So this doesn't really give us, say, an exact time, like a number of when something existed, but it can tell us if we, let's say, find a fossil, perhaps, let's say in this area, in this layer of sediment here, titled B, and we find another one in this section here. Well, we could actually understand that a fossil found in layer B is older than a fossil found in layer A. Well, how do we know this? Well, we know it because if you think about how layers of the Earth would have formed, is a layer down at the bottom would be older than a layer found up here at the top. This would be younger because sediment and earth sort of forms on top of itself, right? And I think we can make sense of that. Also, we should be able to understand that if D is something that happened through layers C and B, then D must be younger than both C and B because it formed inside those layers. And in this case, we can look at this event E, and if we know a little bit about geography, this event here could be what's called like a fault. So like a fault that occurs like during an earthquake where entire layers of the Earth's crust may shift. And so what we can see is that this might be the youngest event that's occurred because this original layer D would have been up in this area, right? And something's happened that's caused this whole section to shift, which would be sort of an earthquake or the shifting of plate tectonics and that sort of thing. So it's a crude measurement in terms of telling how old something is relative to other objects, right? And we can go through that more in class if you have questions, but that's called relative dating, determining the age of something based on the position of a fossil within rock strata or layers of the Earth's crust. So another one is what we call absolute dating. And this one does give us an age, like what we might think of as years and a number associated with it. And it's based on the amount of carbon-14. And so if you remember back to the beginning of the year when we talked about atomic structure and we talked about protons, neutrons, and electrons, and we talked about isotopes and these things in which different atoms of the same element can have a different number of neutrons, which we call these things isotopes. And because life is carbon-based, carbon-14 is a particularly useful isotope in determining the age of a fossil. So certain atoms of elements undergo a natural process of what's called radioactive decay. All right, and this radioactive decay, each isotope will decay at a unique rate. So what this means is just that the particles making up that atom, the protons and neutrons, can undergo changes over time and they can decay. So therefore, they decay at a unique rate. And so if we know that rate at which things decay, then we can work backwards to figure out the age of something. All right, and we call this, when we measure this rate of decay, we measure typically what is called a half-life. And so we measure the rates of decay as half-lives, which is the time it takes for 50% of the material to decay. So let's just use that as an example. Like let's say you start off with 100% of the material, and it doesn't matter. It could be 50 grams, 100 grams, 10,000, it doesn't matter. But just think about it this way, is the time it takes for 50% of that to decay, right, is unique for each substance. And here's some examples of things down below. So potassium-40, uranium-238, these things decay at a rate of billions of years. Carbon-14 decays at a rate of 5,730 years. So in other words, let's say that this is carbon-14. This fossil is found with carbon-14. And in the sample, we've measured a certain amount. Maybe it's 5 grams, maybe it's 10 grams, it doesn't matter. But we'll call that 100% of the carbon-14. Well, if we find this fossil and there's only 50% of that material remaining, then we know that one half-life has passed. And that half-life for carbon-14 is equivalent to 5,730 years. That's the half-life of carbon-14. If, let's say, we found that fossil with only 25%, well, that's half of 50, which means a second half-life has passed, right? A second half-life. Sorry for my pen. But that second half-life means another 5,730 years has passed, and so therefore that fossil would have to be in the neighborhood of almost 11,000 years old. Okay? And this is how we use absolute dating to determine the age of fossils or even the age of rock layers. So if we go back to this example, okay, this is one thing to sort of know relatively the age of these different layers, but we could actually measure the absolute age of these by measuring the substances in these rock layers and using their half-lives to determine how old those rock layers are as well. The last one is what is referred to as our molecular clock. All right, and this is a newer form of dating the age of fossils, but it's referred to as the molecular clock. And this uses a steady rate of mutations in our DNA. So scientists have actually determined the rates at which our DNA undergoes mutations. And so we can use sequences of DNA for different organisms and determine the number of mutations that are occurred and therefore work back and understand the time frame in which this particular organism has perhaps diverged from say a particular ancestor, right? So they're using the steady rate of mutations in DNA. So there's kind of two pieces when we're looking at understanding the past. One is, the fact that life has come onto the planet at various stages in this period of 4.5 billion years. But we also want to think about, well, how did, in fact, the first life evolve? And so in order to think about how the first life evolved, we have to kind of think about, well, how did the first molecules evolve? How did the first molecules that are the building blocks to this life evolve? And so the origin of molecules was first hypothesized by Oparin and Haldane. And these two were working independently of each other, but proposed nearly identical hypotheses. And so collectively, they are known together as the Oparin-Haldane hypothesis, which proposes that at first, the formation of inorganic molecules arose. So inorganic molecules, these inorganic molecules are, for the most part, non-carbon containing. Now you might see the one in there, carbon dioxide, but carbon dioxide is considered a non-organic, non-carbon containing. All right, and so the formation of these non-carbon containing compounds formed, these inorganic molecules, which then may have led to the formation of these more larger, more stable, led to the formation of these organic molecules, what we know of as our lipids and proteins and carbs, and these ultimately pave the way for the formation of our cells and cellular life. All right, so there's a second video that I'd like you to watch, and this is by the two individuals, Miller and Urey, who actually tested this hypothesis by basically performing an experiment in which these starting materials, which would have represented early atmosphere of Earth prior to life existing on the planet. And their experiment looks at how these inorganic compounds under the right conditions can give rise to these organic molecules. So if you pause this and watch that, that'll wrap things up, and you can find that video back here in our third video, the Miller-Urey experiment. See you in class.